All right. The next thing we are going to look at is something called rotational work. Now, you have to remember what work is. What happens when when a person performs work on an object? Now, when you perform work on an object, you apply a force. In this case, you apply a force F, whatever force you're applying, then this force causes this particular object to move a certain amount of distance. S. Are we clear? When you perform work on an object, so you perform work on an object, you have to apply a force F, and this particular force causes an object to move in a straight line S. Is that clear? The result of all these, the result of you performing work is that this particular object you're performing work on is going to end up having motion. If an object has got motion, it means that it has got linear momentum, and as we have seen, if it has got linear momentum, it has got kinetic energy. So the end product of doing work is the transfer of energy from you, the person who is performing work, to this particular object which you are performing work on. If you recall from our work energy theorem, the amount of work you do is going to be equal to the change in kinetic energy which the particular object is going to experience. That is why work is done. We do work so that we transfer energy from ourselves, the people performing work, to the particular object on which you are performing work on. So the object you're performing work on is going to end up having gained kinetic energy. The amount of kinetic energy which the particular object is going to gain depends on how much work you have done. That is according to the work energy theorem. This is when we were talking about work done in a straight line. Is that clear? And do people still remember about what we said about work? Hello, I need confirmation. Is it clear on what this is, what it's doing?
Yes, it's clear.
Now the same thing applies with rotational work. We have seen that there is something called rotational kinetic energy. Rotational kinetic energy being given by KER equals to half a moment of inertia omega squared. So when you perform rotational work, this rotational work which you have performed, and of course, since for you to perform work, you need force and displacement, a similar thing applies when you are performing rotational work. Now, when you perform rotational work, instead of you applying a force, what you need is a torque. You need your force to produce a turning effect. If you apply a force, then this force you're applying does not produce a turning effect, then you have no torque. If you do not have any torque, then there is no work you can perform. So apart from having a torque, which is the secular equivalent of force, you also need this torque which you are applying to cause a displacement. You need this torque to cause an angular displacement. You need this torque to rotate a wheel. We need this torque to rotate a cycle. Like when you are pushing a tire, or maybe you're pushing a tire, or you're just spinning something. When you're spinning something, you are performing rotational work, because the end result of this rotational work which you're doing is that this particular object you are spinning is going to end up gaining rotational kinetic energy. As you perform your rotational work, the object you are spinning will end up having rotational kinetic energy. Are we clear? So you apply a torque. This torque causes an object to rotate, and when this object is rotating, it undergoes an angular rotation, an angular displacement, theta. So in that case, the amount of energy you have transferred to this particular object which you are spinning is what is referred to as rotational work. The rotational work is equals to the torque multiplied by the angular displacement. Work also has got units of joules. Are we clear? So in this case, the applied torque, you apply a torque about an axis of rotation. So when you apply this torque needs to cause this particular object to spin. If there is no spinning, then there is no torque because there is no turning effect. And you have to measure how much angular displacement this particular object is going to spin. So basically that's what rotational work is. Are we clear? Rotational work,
yes, it's clear.
Rotational work results in, when you perform rotational work, there is going to be a transfer of rotational kinetic energy to this particular object, and it has to undergo an angular displacement. The other thing is power. When you are in a straight line, we know that we have looked at power. At the same time, we looked at work. Power is basically how fast you are doing work. So power is basically work divided by time. But we also saw an expression of power given by this. Power is equals to the applied force multiplied by the average velocity. Applied force multiplied by the constant velocity with which this particular object is going to be moving. So when you apply a force on a particular object, and this force causes an object to move with a certain average velocity v, or a constant velocity v. Usually when you apply a force, there is going to be a change in velocity. So the force, the velocity we are talking about here, when there is a force present, there is going to be an acceleration. The force we are talking about here, this v, is not the initial velocity, it's not the final velocity, but it is the average velocity. It's u, initial velocity, plus the final velocity divided by 2. This v, it is the average velocity. That's why it is a constant. So we're supposed to say constant average velocity v. So when you apply a force F, then this particular force causes an object to move with an average velocity v. Then the power which is dissipated, the power you spend is P is equals to the force multiplied by the average velocity. Are we clear? This is from the previous classes on work, energy, and power. Is this clear?
Yes, sir.
So similarly, you can also perform power. There is power which in the case of rotational motion. So in the case of this, so we translate this thing, we shift it from straight line motion into rotational motion. So when you do that shift, in place of F, which is the force, we are going to have torque there. Then in place of V, which is the average velocity, we are going to end up with omega. So in this case, the power is equals to the torque multiplied by the angular velocity. So where torque is the torque applied torque about the axis of rotation, and omega is the constant angular velocity with which this particular object is going to be spinning. So if you apply a torque, then this torque you have applied causes an object to spin about its axis of rotation with angular velocity omega. Then the power, in this case, the power which is transmitted due to your torque is equals to the product of the torque multiplied by omega. Is that clear?
Yes, sir.
Okay, so that's about power. So if you know what the power is, there is maybe some, I don't know, a motor with a certain amount of power, then you know how much it's whatever it, if something has got a certain amount of power, then it's causing some stuff to spin at a certain angular velocity. You can always find out how much torque is there. Okay. Okay, so we have got an example. Example number 10. A motor runs at 20 revolutions per second. So this 20 revolutions per second, this is a measure of the angular velocity and supplies a torque of 75 Newton meter. What horsepower is it delivering? Now, horsepower is a unit, another unit of power. Power can be measured in watts, but it can also be measured in terms of horsepower. So in this case, we have our angular velocity, which is 20 revolutions per second. So we need to change these 20 revolutions per second into radians per second. So in that case, our 20 revolutions per second in radians per second, we're going to have omega, which is equals to 20 revolutions per second. That's going to be 20 revolutions divided by 1 second. Then you end up multiply with the conversion factor 2 pi radians divided by 1 second. So one revolution. So one revolution here, this revolution bit here, the revolution bit here, and the revolution which you have here, they will cancel out. So you end up having 20 times 2 pi radians divided by 1 second. So you end up having an angular velocity which is equals to 126 radians per second. So this is our angular velocity, 126 radians per second. We have been told that the torque which is being supplied, the turning effect which in this case is 75 Newton meter. So we can work out what the power is which is being transmitted. The power P is going to be equals to the torque multiplied by the angular velocity, which is equals to 75 Newton meter multiplied by 126. Then we end up having a power which is equals to 9,450 watts. Now, this is our power in watts, but we have been asked to find the power in horsepower. Now, for you to do that, since a horsepower is also a unit of power, 1 horsepower, 1 HP is equivalent to 745.7 watts. So we can convert our power, which we have in watts here. So pure power in watts, which is 9,550 watts, converted into horsepower. So you end up multiplying 1 horsepower divided by 745.7 watts. So what you're going to end up having here is that our watts here and that there will cancel out. So you end up having 12.7 horsepower. So this is going to be your power in horsepower. Are we clear?
Yes, sir.
Okay. Next, there is another example. Example number 11. An electric motor runs at 900 revolutions per minute and delivers 2 horsepower. Okay. How much torque does it deliver? How much turning effect does it deliver? So in this case, we know that power is equals to the torque multiplied by the angular revolution. Now, the angular revolution in this case, angular velocity in this case is your 900 revolutions per minute, and the power is 2 horsepower. So in this case, our power, which is in horsepower, 2 horsepower, is equal to 2 HP multiplied by 745.7 watts divided by 1 HP. So the HP and this HP here, they will cancel out. So we end up having our power in watts as 1491.4 watts. So this is our power in watts. The other bit which we have, which we need to change, is this. We've got 900 revolutions per minute. So this 900 revolutions per minute needs to be changed into radians per second. So in that case, our 900 RPM is going to be 900 revolutions divided by 1 minute. So that's our 900 revolutions divided by 1 minute. So we try to change the revolutions to radians. So that's going to be 2 pi radians divided by 1 revolution. So the revolution here will cancel out that revolution. Then we multiply by 1 minute divided by 60 seconds. So the minute which we have here is going to cancel out this minute. So at the end of the day, we're only going to have radians per second left. And if you work out 900 times 2 pi radians times 1 divided by 1 times 1 times 60, you end up having 94.2 radians per second. So this is how much the...
excuse me, sir.
Yes.
Sorry, but I think you are too fast today.
Am I too fast?
Yes, sir.
You don't have the notes?
Yes, sir, you're too fast.
You don't have the notes? You have not downloaded the notes? Are you seeing the notes for the first time?
No, I have them.
Yeah, so I expected people to go through these notes so that you can ask questions where you are you're not sure about what's going on. So what we're doing here is we are changing the power, which is in horsepower, we're changing it into watts, which is what we've done here. Here we're changing our angular velocity, which is in revolutions per minute. We're changing that into radians per second, which is what we've done here. This process we have done before. It's not the first time we're changing revolutions per minute into radians per second. I'm sure you agree with me with that. So people should be able to understand what we're doing here. Okay. Is there any other question? Okay. So next, we have our power in watts, 1,491.4 watts. We have our angular velocity in radians per second. So in this case, we're looking for the torque, which is that. So we make the torque the subject of the formula. When you do that, so we divide both sides by omega. When you do that, we end up having torque is equals to power divided by omega. So in our case, our torque is going to be, the power is 1,491.4 watts, and our angular velocity is going to be 94.2 radians per second. So in this case, your torque is going to be equals to 15.8 Newton meter. Is that clear?
Yes, sir.
Okay. Example number 12. A 0.75 horsepower motor acts for 8 seconds on an initially non-rotating wheel having a moment of inertia 2 kg meter squared. Find the angular speed developed in the wheel, assuming no losses. So the first thing we have is we have the power in horsepowers. So the power is 0.75. So in this case, we change our power. Our power is equal to 0.75 horsepower. And when you do this conversion, you should end up with this. You end up with 559 watts. Now, how much work is done? We know that power, from this expression which you have here, we know that power is how fast you're doing work. Power is equals to work divided by time. So using the definition of work divided by time, we can find out how much work has been done. So in this case, the work done, how much rotational work has been done. You can find out the amount of rotational work which has been done. So in this case, the work done is equals to the power multiplied by the time, which is just 8 seconds in this case. The power is what you have here, 559 watts multiplied by the 8 seconds. So this gives us the amount of rotational work which has been done, which is 4,472. This expression is from the definition of work. Sorry, from the definition of power. Power is equals to work divided by time. The work done divided by the time taken. So in this case, we just make the work the subject of the formula. We end up with power is equals to, work is equals to power multiplied by time. Are we clear?
Yes, sir.
Okay. Now, if this is the amount of work which has been done, then we are talking about rotational work. And as I was saying earlier, what does work do? Work transfers kinetic energy. When you perform work on a we're told this was a non-rotating wheel. When you perform work on this wheel, then it starts to rotate. As you perform this work, this is how much work you have performed. This wheel is going to gain rotational kinetic energy. Every time you perform work, if it's on a flat surface, if you perform work on an object which is on a flat surface, that object is going to get kinetic energy. In the case of a wheel like this, when you perform this work, this non-rotating wheel is going to gain rotational kinetic energy. Is that clear? So in our case, this is the amount of work which has been done, and so this work which has been done is going to show up as rotational kinetic energy of the wheel using the work energy theorem. So in this case, the work done is going to be equals to the rotational kinetic energy, and rotational kinetic energy is equals to half moment of inertia then omega squared. Okay, so in our case here, when we using the work energy theorem, so this rotational kinetic energy bit is equal to the work done. So in our case, we end up having half moment of inertia omega squared is equals to 4,472 joules. We have been given the moment of inertia of the wheel as 2 kg meter squared. So in that case, when you put that information there, we put this information in here, 2 kg meter squared multiplied by half. This is our moment of inertia. So we end up with this 2, and that 2, we just end up with 1. Then if you divide both sides, you end up with omega squared is equals to 4,472 joules divided by 1 kg meter squared, which is going to give you 4,472 radians squared seconds squared. Good. Then if you take the square root on both sides, you end up with omega is equals to the square root of 4,472 radians squared seconds squared. You end up with omega is equals to approximately 67 radians per second. So the speed which our wheel gains, or our angular velocity of the speed of the wheel in this 10 seconds is going to be 67 radians per second. Is that clear? We have used, what have we used? We have worked out the power, then using the time, we have worked out how much work has been done. But the physics is us using the work energy theorem here. The physics is on the work energy theorem. The realization that this rotational work which has been done is also equal to the kinetic energy, the rotational kinetic energy gained by the wheel. when you equate how much rotational work is being done to how much kinetic energy, rotational kinetic energy, the wheel is going to gain, that's where the physics is. So the work done and the rotational kinetic energy are related. According to the work energy theorem, they are the same. Their magnitude is the same. Are we clear?
Yes, sir.
Yeah, so once this bit is done, then the rest is easy to do. So the physics is realizing that when you perform rotational work, you are actually transferring rotational kinetic energy onto this particular object you are performing rotational work on. That's where the physics is. Okay. Okay. The next item we have to look at is something called angular momentum. Now, if you recall our discussion, our talk about what linear momentum is and how we find linear momentum. Linear momentum, which denoted P, was defined as the product of mass times velocity. But what does mass times velocity actually measure? Linear momentum measured the amount of motion which an object was undergoing in a straight line. That's what linear momentum measured. It measured how much motion an object was undergoing when it's moving in a straight line. And how do we get that amount of motion? By multiplying the mass of this particular object times the velocity. The same thing can be done when we talk about an object which is spinning on its own axis or it's moving in a circle. We can find out how much rotational motion is happening. So, angular momentum measures the amount of rotational motion which a rotating body is undergoing. Same as linear momentum. Angular momentum does the same thing. It measures the amount of rotational motion which an object is undergoing. So angular momentum, denoted L, is the same way we work out linear momentum. Okay? Instead of M, we put moment of inertia, and instead of velocity V, we put omega. So angular momentum L is a product of the moment of inertia being the mass which an object has when it's undergoing rotational motion, multiplied by the angular velocity which a particular object has as it's rotating. Is it clear what momentum measures? Whether it's linear momentum or it's angular momentum, momentum measures the amount of motion which an object is undergoing. So in the case of angular, we are measuring how much rotational motion, how much spinning, if you've got a wheel rotating about an axis, how much rotational motion is happening. And the amount of that rotational motion is going to be a product of the moment of inertia, which is the mass which an object has when it's spinning on its axis, multiplied by the angular velocity of this particular object. Are we clear on what momentum is?
Yes, sir.
Whether it's linear momentum or it's angular momentum, momentum measures the amount of motion which an object is undergoing. So if you have got an object, then this particular object stops rotating. The angular velocity is equal to 0. Then the linear momentum is going to be equal to 0. So the angular momentum is going to be equal to 0. You can only have angular momentum when your object is in motion, or when your object is undergoing rotational motion. Of course, the object needs to have a certain amount of moment of inertia for you to do that. Okay, so let's have a look at an example which has to do with angular momentum. Example number 13. A 500 gram uniform sphere of 7 centimeter radius spins at 30 revolutions per second on an axis through its center. Find its angular momentum. So basically, they are asking us to find what is the amount of rotational motion which this particular object is undergoing as it spins on its axis at 30 revolutions per second when you've got a sphere of mass 500 grams in radius r. Angular momentum, which is the amount of rotational motion L, is given by L is equals to the moment of inertia multiplied by what the velocity is, the angular velocity in this case. So since we know the mass of we are talking about the sphere, and for a sphere, the moment of inertia, if you go back on our table, the moment of inertia for a sphere I is equals to 2/5 the mass of the sphere multiplied by the radius of the sphere. This is how you get the moment of inertia for a sphere. So it's up in our table at the back. Okay, so our mass is 500 grams, but this mass 500 grams, we need it in kgs. So our mass is going to be in kgs, 500 grams in kgs is 0.5 kgs. Our radius is 7 centimeters, and this radius in meters, R is going to be 0.07 meters. So that's the radius of the sphere. So with this information, we can find what the moment of inertia is. Remember what moment of inertia is. Moment of inertia is the rotational inertia, the resistance which a mass offers when you try to spin it. So the rotational inertia which an object offers. So that moment of inertia, which is denoted I, so now that we know, and we know that this moment of inertia depends on the shape of the object. So now that we know our object is a sphere, a uniform sphere, then we just substitute so that we can find what the moment of inertia is. I is equals to 2/5, mr, that's going to be 2/5, then the mass 0.5 kgs, and the radius 0.7 meters squared. So we end up having I is equals to 9.8 times 10 to the power minus 4 kgs meters squared. So this is going to be our moment of inertia. So we have one part, or we have one element of what we need to work out the angular velocity, angular momentum. The moment of inertia, we have it. The other bit is the angular velocity. We have an angular velocity which is 30 revolutions per second, but we need this angular velocity in the radians per second. So when you convert, your angular velocity omega is equals to 30 revolutions per second is going to be, that's going to be 30 revolutions divided by 1 second. So you end up having 30 revolutions per second multiplied by 2 pi radians per revolution. So this revolution and that, they'll go. So you multiply 30 times 2 pi radians, then you divide by 1 second. So you're going to end up with angular velocity of 188.5 radians per second. So we have our angular velocity this side, we have our moment of inertia here. So we have everything we need to work out what our angular momentum is going to be, L. So in this case, as you can see, there's a mistake. Instead of I here, it's supposed to be L. L is supposed to be equals to I omega. So that's going to be 9.8 times 10 to the power 4 kgs meter squared multiplied by this bit here. So you end up having your L. So you make a correction in notes. Not this I here, which is appearing as I, is supposed to be your what? It's supposed to be your angular momentum. So L, this side is going to be do that. So you end up having this. So your angular momentum is 34.8 Newton meter. Like that. So make a correction in your notes there. Are we clear? How you work out angular momentum?
sir.
Okay. Now, if you have angular momentum, and remember what angular momentum is. Angular momentum measures the amount of rotational motion. This rotational motion which this particular object is undergoing, well, can stay the same, or it might not stay the same. If the angular momentum stays the same, it means that there is no change in angular momentum, right? The change in angular momentum is equal to 0. The same way, if you recall, we had impulse. Impulse, when you're looking at linear momentum, then we expressed Newton's second law of motion in terms of linear momentum to have F is equal to the change in linear momentum, delta P, divided by that. So we came up with a physical quantity called impulse. Impulse, which is the change in linear momentum, was defined as the force multiplied by the time. And if there is an impulse, basically impulse measures how much motion an object has gained as a result of the presence of a force for a certain amount of time, or how much motion an object has lost. Linear momentum measures the amount of motion which is there. Impulse measures the amount of motion which has been gained by an object as a result of a force acting on this particular object for a certain amount of time. Is there a question?
Yes, sir.
Yes.
Sorry, can I take you just back for a moment? I'm quite behind on the 34.8 kg per meter per second squared. I'm confused on how it came about.
What do we have? We've got radiance this side, moment of inertia this side. Where is what? So what's with the units? What's with the units? What's the units? Kg is meter second squared, then the second squared. So we end up having what? We end up having kg what have we done? I'm not sure what I've done here. I'll need to look at this back again. I'm not sure what I have done with the units. So there's a kg, there's meter squared here, there's a meter squared here. Okay, then of course the radian is silent, so which means we're supposed to have a second, just one. Then what else do I do? I separate the meter squared. So I've got this bit here, I've got this bit here. Okay, then how am I trying to create a Newton? Okay, what have I done? Wait a second. So if I create a Newton, I need to introduce another second. I need to introduce another second at the bottom and on top. So there's supposed to be Newton meter. I don't know what I think there's a second which is missing. There's something which is missing here. There's a second which is missing somewhere here with what this thing which I was trying to do here. Something like a second is missing, but anyway, that can be fixed later. Okay, so I'll try to see try to relook at this. Okay. Yeah, thanks for bringing this to my attention. Okay, so let's move on to the angular impulse. So like I was saying, impulse measures how much motion an object has gained or how much motion an object has lost. And remember, motion is measured in terms of in terms of linear momentum or in terms of angular momentum. So the same thing applies with angular impulse. Angular impulse is the amount of linear momentum, so the amount of angular momentum or the amount of rotational motion which an object is going to gain as a result of a torque acting on this particular object for a certain amount of time. So you should have a torque which is acting on this particular object for a certain amount of time. So in that case, that's what you have here. This is the equivalent of Ft in a straight line, force multiplied by time. So instead of force, we end up putting torque here. Torque multiplied by time is going to be equals to the final angular momentum minus the initial angular momentum. This bit here is just the change in angular momentum. So angular impulse, torque multiplied by time is just equals to the change in angular momentum, which is equals to the final angular momentum minus the initial angular momentum. Tau is applied torque about an axis of rotation. T is the duration for which this torque is present, and LF is the final angular momentum, and Li is the initial angular momentum. Yeah. So yeah, like this. Now, apart from this expression, we know that angular momentum can be expressed in terms of the moment of inertia and omega, like we have up here. Angular momentum, L, is equals to moment of inertia multiplied by the angular velocity. So you can rewrite this expression. You can write this expression in terms of this. You can write like this. Angular impulse is equals to the moment of inertia multiplied by omega f minus your moment of inertia multiplied by omega I. If you go further with this expression, as we are going to, I think, show, yeah, so this bit here, where I is your moment of inertia, then omega f is your what's referred to as your final angular velocity, and omega I is your initial angular velocity. If you, this I which is here and this I, moment of inertia, it's the same object you're talking about, so the I is the same. You can factor out the I, then if you divide both sides by this T, if you divide by T this side, if you divide by T this side, you're going to end up with I. Then you're also going to have this omega f minus omega I, which is the change in angular velocity divided by the time, which is going to give you the angular acceleration. So you end up with what you have always had. Torque is equals to I alpha. Okay. Okay, now let's see what we have here. So basically, I think that's what I'm trying to say here. Revisiting the relationship between torque, angular impulse, angular momentum, and angular acceleration. Okay, so let's have a look at this relation. So the torque applied on a spinning object can be expressed in terms of the rate of change of angular impulse. So what I'm trying to say is that you can express the torque in terms of angular impulse, and in this case, so this is your torque, okay, but the other bit here, you can express it, this is basically torque, this side and this side is torque, but this other bit here, we can express this torque in terms of angular impulse, and we can, so that we multiply torque, so you divide by T, multiply by T, and you divide by T. Basically you haven't done anything, it's just the same thing. So you decide torque times T, so you end up with torque times T on top, then you divide by T. But what you have created here, when you multiply the torque times T, that is our angular impulse, this thing, our angular impulse. Then that. Now we know our angular impulse that is equals to this bit. Our angular impulse is equals to the final angular momentum minus the initial angular momentum, which is also equals to moment of inertia I multiplied by omega f minus moment of inertia I multiplied by omega e. So this bit here, our angular impulse, basically that's what I'm trying to explain, is also equals to this bit here. Okay. So if you get, for this expression, which you have there, you replace with this. So you end up having this bit, the torque. Your torque is going to be equals to moment of inertia multiplied by final angular velocity minus moment of inertia multiplied by initial angular velocity divided by the time. Then you factor out the moment of inertia, so you end up having your torque being equals to I, then open bracket your final angular velocity minus your initial angular velocity divided by the time. Now in this case, this bit here, omega f minus omega I divided by time, so you can have torque is equals to I, this bit here, this is your alpha, your angular acceleration. Basically you have torque is equals to I alpha. This equation number 24, as you can see, torque is equals to moment of inertia multiplied by alpha, is Newton's second law of motion for an object which is undergoing rotational motion about an axis of rotation. So we did not just come about with the substitution of saying, no, in place of f you put tau, in place of m you put I, in place of alpha you put a, you put alpha angle. The thing is sound. Okay, are we clear?
Sure, sir.
Okay, so that's basically, so you can have all the confidence as you use these expressions to express your torque. Basically, torque itself is equals to moment of inertia multiplied by alpha, so it depends on what you want to do. So this is if your if your angular velocity changes, it means that there is change in linear momentum. If this bit changes, if omega f changes, you've got omega f, you've got omega f, you've got omega I, then you multiply your omega f times omega I, and like that, so you end up having this whole thing of having angular momentum and change in angular momentum. So it depends, really, it's up to you which approach you want to take when you're trying to look at these questions. Okay. All right, number 14. An airplane propeller has a mass of 70 kgs and a radius of gyration of 75 centimeters. Find its moment of inertia. How large a torque is needed to give it an angular acceleration of 4 revolutions per second squared? So in this case, the moment of inertia, the mass is 70 kgs. The radius of gyration we've been given. This radius of gyration is 75 centimeters. So K is 75 centimeters, which is equals to 0.75 meters. So with this information about mass of the propeller and its radius of gyration of 0.75 meters, we can work out what the moment of inertia of the propeller is. The moment of inertia of the propeller in this case is going to be I is equals to the mass multiplied by the radius of gyration squared. So we're going to end up I, moment of inertia 70 kgs, multiplied by 0.75, the whole thing squared. So we end up with our moment of inertia I equals to 39.4 kgs meter squared, like that. We are trying to find the torque. So we have our moment of inertia here. We're trying to use this relationship here. We're trying to use this. We're trying to find torque. We have moment of inertia. We have got acceleration, angular acceleration given in the revolutions per second squared. So we change our acceleration. Our acceleration 4 revolutions per second squared. We want to change our acceleration into radians per second squared. So in that case, alpha, which is our acceleration, is 4 revolutions per second squared, which is equals to 4 revolutions divided by 1 second squared. So we change this revolutions into radians. That's going to be 2 pi radians divided by 1 revolution. So the revolution, this one, and that, they go. So you end up having 4 times 2 pi radians, which is going to be 25.1 radians per second squared. So this is your what's this? This is your angular acceleration. That. Next, now we can work out our torque. So our torque, tau, is going to be equal to the moment of inertia multiplied by alpha. So in this case, our torque, tau, is going to be 39.4 kgs meters per second squared multiplied by 15.1 radians per second squared, and we can end up having our torque, which is equal to 989 newtons meter. This. So that's going to be our torque. Okay, so we are on page 19. So there is still some stuff which is left. Since the other quiz has been moved to 30th, we can leave a bit of something for next week on Monday. Do we agree? There is no need for us to press ourselves too much, because we already, if you recall, we already pressed ourselves too much on Monday. We added an extra 30 minutes to the lecture we had on Monday. And since the other bit of the quiz has been moved to 30th, I think it's okay that we stop here. The other bit which is left, this, how many pages? I think 5 pages, maybe a few pages left. We can look at them on Monday. Are we clear?
Sure, sir.
Yes, sir.
Okay, unless any questions? Are there any questions? Okay, if there are no questions, I'll stop sharing and I'll stop the recording. So as usual, the video is going to be uploaded to YouTube. The link is going to be shared in Moodle so that you can watch